In the last video, we developed the energy for our simple model of lateral torsional buckling. The energy was given by V of phi theta. Phi and theta are the degrees of freedom here, the torsion and the out-of-plane bending. 1/2 kt phi squared plus 1/2 kb theta squared plus Bl sine phi sine theta. Now, equilibrium is the first derivative of the energy. So we have two equations of equilibrium, dV by d phi equals 0 and dV by d theta equals 0. Again, as we did in the simply supported column with 3 rigid links, we are not, but unlike the cantilever column with 1 rigid link, we're not interested in exploring the post-buckling behavior, but we are just content with assessing the stability of in-plane equilibrium. So we're trying to find out at what load the in-plane equilibrium transitions from being stable to unstable. Stability is given by the second derivative of the energy. So in this case, the second derivative is d squared v by d phi squared, d squared v by d theta d phi, and so on, which by direct calculation is the matrix on the right. If we evaluate this second derivative at the 0, 0 equilibrium point, we get the matrix KT, PL, PL, KB. Now the reasoning is identical to what we did in the case of the column. For small enough p, this matrix is positive definite. For example, for p equals 0, it's clear that this matrix just has KT and KB on the diagonal and is positive definite. So for small enough p, this matrix is positive definite. And as p increases, for some value of p, one of its eigenvalues will just become 0. And when this happens, for such a p, there is a vector phi theta such that the matrix KT, PL, PL, KB times phi theta equals 0. That means that matrix has a 0 eigenvalue. Another way of thinking about it is this matrix has a non-zero solution for 0 right-hand side. And we know from linear algebra that for this to be the case, the determinant of this matrix must be 0. So the determinant is KTKB minus P squared L squared. Solving, we get critical buckling load is 1 over L times the square root of KT times KB. So for loads less than this, the beam will not buckle out of plane, and for loads greater than this, the beam will buckle out of plane. Now, the actual assignment involves using a model that has multiple links connected by torsion and out-of-plane bending springs. So the process is very similar. Of course, if there are n links, then the model has not 2, but 2 times n degrees of freedom. And so the process of working out the kinematics so that you can determine the height of the load to calculate the energy is more challenging. But other than that, conceptually, that is very similar to this and the column.